Log on, tune in, find out. Another good idea from Cambridge.
So I hope you are not conferenced out already. I'll try to keep it light as much as possible. So I'm going to talk about GP based emulator for a deterministic simulator. Okay. You'll see that in my title there are terms like interpolation. So I'll try to argue that what I want to do here today is build an interpolator. Okay. Although some people will say that every computer simulator has some noise in it, some uncertainty, but sometimes you'll see that experimenter, in my case oceanographer, asked me that you have to interpolate the data. Okay. So I had to think about getting a GP to interpolate the data. You see that theoretically it should be pretty straightforward, but apparently it's not so straightforward. So we'll see. So GP, just a quick review, all of us know a lot about GP. So I'll assume a constant mean mu and then standard multivariate normal distribution. GP has nice features like predictor and the associated uncertainty. We'll talk a little bit more about the details of this functional forms here later. Fitting the GP part is kind of important. Okay. Some of us use Bayesian techniques, some of us use likelihood based methods for fitting GP model. I am using likelihood based methods, but you can use Bayesian approach. For likelihood method, we will assume the standard Gaussian correlation that I use here, but you can use other correlation structures if you want to. For the rest of my talks, it doesn't really matter a lot which correlation function you use, as long as you are using, well, I won't say any correlation function because I don't know, but at least power exponential correlation function. Okay, I'll say that. So for fitting the GP model, what do we do? We compute this likelihood expression, or minus log likelihood, minus 2 log likelihood, and optimize this guy, minimize this guy over the theta space, because we can do the profiling by substituting mu hat and sigma square hat. So basically we have to compute this guy for whole bunch of theta and pick the best. Okay. Nice and simple. So I have a simple example here, thanks to Roshan and Herbie. So yesterday afternoon I went and I implemented this example. I liked it. I didn't have a 1D nice example for the illustration. I had 2Ds, but I thought, okay, this is pretty cool. So what we have here is 5 points chosen using maximal Latin hypercube design, just a space filling. I'm just illustrating that GP fits give you pretty nice interpolator. As you can see that there are 5 points that are passing through the emulator, and it has nice uncertainty intervals here. So very easy. Are we done here? Not so fast. Implementation of this is not so easy. What do we have to do? What's not easy here? That when we try to compute this likelihood, computation of determinant of R and R inverse are not so stable. Okay. And the reason is that if you have, so in the last picture you can see that the data points are too far away, so we didn't run into any problem. But as soon as some of the x's are too close to each other, then the correlation matrix become near singular. Okay. And well, although since it's a deterministic process, we are not going to replicate our trials, but the points can be close, especially if you are working in a lower dimension space and you have too many data points. Okay. Then this problem will occur no matter if you use another power here or Well, I would argue that if you use other correlation structure based on distances, then also if you have two x's, two data points that are close together, then two of the rows of the R matrix will be similar, and so the correlation matrix will be ill-behaved. Okay, and so you'll run into this problem. So the determinant will be very erratic, and the inverse calculation will be very erratic. And so if you guys have plotted the likelihood for theta close to 0, you can't have theta equal to 0, then definitely it will be a J matrix or matrix of all ones, and you can't invert it. But theta close to 0, then you'll see that near theta equal to 0, the likelihood is very ill-behaved. Okay, and then when you go away from 0, then it's fine. So the problem occurs when theta is, so this theta parameter, hyperparameter I'm talking about, if that quantity is close to 0, then the likelihood or the computation of these two guys are not stable, or if the xi's are kind of close to each other. So this is a big computational issue that we run into. So for the rest of my talk, I'll briefly talk about near singularity of R, and under what circumstances we get near singular matrices. Is that really common? How common it is? And then we will talk about the popular approach that probably all of us or a lot of us use to overcome this problem of near singularity, that is just using a small nugget, and sometimes we estimate the nugget with other parameters by using, say, maximum likelihood, or we throw a prior on it, and then we go ahead and do our own problem, whatever bigger problem that we are trying to solve. That's okay if we assume that there is a little bit of noise, because as soon as you introduce a nugget, it will over smooth. Okay, the data will not be interpolated anymore. The emulator will be a smooth one. Okay, as I will show you. So what we do, what we suggest is, instead of estimating it using maximum likelihood approach or using some prior Bayesian technique, maybe we should choose our nugget or delta a little bit carefully. Okay, so we'll talk about that, how carefully. But even if you, no matter how careful you are, as soon as you use a nugget in the model, you will not have an interpolator anymore, and we wanted an interpolator. So we propose a new iterative approach, and that converges to an interpolator relatively quickly. I'll show some examples, and then with some conclusions remarks. So near singularity. What is near singularity and how do we quantify it? We can quantify near singularity using this formula kappa of R, and that's matrix norm of the correlation matrix R times matrix norm of the R inverse. In L2 norm, we can pick different norms here, but in L2 norm, this is just the ratio of the eigenvalues, maximum over minimum eigenvalues, and this quantity, what are the possible values, or how these quantities look like. If we just try a bunch of values, extreme values, then we will see that this kappa of R, the ratio of the eigenvalues, will always be positive, because we are talking about positive semi-definite matrices or positive definite matrices. So this quantity will always be positive. This will be 1 for identity matrices. Okay, meaning if the correlation matrix is very, very nice, the best you can get is R independent, no cross correlation. It will be infinity if you have 2 points that are exactly equal, two xi's are exactly equal, then you have 2 rows that are same in R matrix. So one of the eigenvalues will be 0, and suddenly it becomes infinity. The worst case, that we cannot get points they are exactly equal but too close. So this kappa R or condition number will be very, very large, okay, close to infinity. So just to get some feel about this condition number. So we tried to see that, tried to get a feel about how often we run into near singularity, okay, in real life. So, well, with simulated data in my case. So what I did here is for space filling designs. So I just generated a whole bunch of designs using Latin hypercube. So on here we have n over d, and over here we have d. D is the input dimension, and n over d, just because I'm doing so that. So for example, this corner here talks about 6-dimensional space and 300 points. Okay. Similarly here, this point here is 2-dimensional space with 20 points and so on. Okay. So for each n and d combination, I generated 5,000 matrices using random Latin hypercube, and I just computed the proportion of cases which was near singular. How do I observe that it's near singular? So MATLAB has a function called chol for Cholesky decomposition. It returns two arguments, u and p, where u is the upper triangular, the lower triangular, upper triangular matrix, and this quantity p, if p is greater than 0, that means it's near singular. And if p is equal to 0, then it's well behaved. Yes.
So you substituted in a correlation parameters for this in order to get.
That's right. Yes. So I had to pick my theta, right, for computing r, because r has a fixed design and the theta. So design I'm generating through here, random Latin hypercubes, and theta, as I've told you that for large value of theta, we don't have to worry too much about the near singularity. So I generated theta from exponential 1. Okay. So near 0, and so this here is the average contours here. The contours of the average proportion or the proportion. As we can see here, so this number goes from 0.05 to 0.9. So this point here says that if you have 70 point designs in two-dimensional space, then 90% of the correlation matrices will be ill behaved for small values of theta. Of course, if we pick theta very large, then we'll be okay. Okay. So this problem occurs quite often in small dimension. As you can see that for larger dimensions, we are okay for reasonably big design point, and that's expected again, because if we have a large dimension, then we really need a lot of points, okay, to fill the space, okay, because the volume of void increases with the polynomial order of d. So this problem is quite common in low dimension space. Popular approach is to substitute r with r delta, and r delta is r plus delta I, just add through the diagonal elements of r, and this is equivalent of adding a nugget in the model, but we are talking about only a numerical fix. Okay, we are not talking about adding a noise in the term. So this is equivalent of replacing r inverse by r delta inverse, and but we have to pick delta that is big enough so that this is not near singular anymore, not ill conditioned anymore. Okay. So how do we estimate delta? Well, the common procedure is to estimate it along with other likelihood parameter, other theta parameters, but we got to be careful, because when we are optimizing, think about actually implementing it. When you are optimizing it, picking delta values, then you can't really start from 0, okay, because delta equal to 0 will crash, right? So you have to start from a little bit big. How big? Is 10 to the minus 5 big enough? Is 10 to the minus 10 big enough? How big is that? So in reality, when you start about implementing it, then you pick ad hoc boundary to begin with, or how do you pick? Okay, so that's a problem. That's a problem. So we'll talk about some of these things. In this example, I said that okay, this is, so here is the same toy function that I'm using with 20 points, equally or not equally spaced, but Latin hypercube, maximum Latin hypercube, and I said that I want the optimization in delta 10 to the minus 5 to 1. Okay, and I tried it for delta equal to 0, and of course it crashed. Okay, for small values of theta, I could have tried for really large, but for small values of theta it crashed. So I fixed this for optimization, and I got this MLA fit, and this blue solid curve is the fitted GP model. As we can see that it's so much smoothing going on. We cannot interpolate this based on this. So the question is, do we really need this 10 to the minus 5 as the lower bound? How lower can we get? Okay, we'll talk about that. So go back to this near singularity again, try to look into it a little bit deeper, and we see that okay, we need a small delta, as small as possible, but it has to be large enough so that this quantity is well behaved. So taking a look at the same plot again, and we said okay, let's take a look at the condition number here. Okay, so for the similar setup here, n over d and d for 5,000 matrices, I computed the average condition number and then the log of that, okay, natural log of that. So these numbers go from 10, 15, 20 up to 40 here, and these are log of the condition number, average log of the condition number. We can, and that's what the shaded region is here, the number that is bigger than 25. Okay. So, we can see that if condition log of the condition number is bigger than 25, then we run into near singularity problem. If that number is less than 25 roughly, then we are okay. Okay. So, I use that as a rule for thinking about a lower bound for nugget. Okay. So, we say that okay, let us think about a threshold A. Okay. In this, according to this, it suggests 25, but if we wanted to be safer, we could have picked 20, or we could have picked 15 if we wanted it to. Okay. So, this is for again these two plots are for maximal random Latin hypercube designs. Okay. If you are working with a different design, for example, sequential design and so on, we can pick a different A. Okay. So, we use this that log of condition number of R less than equal to A will give us into a safer zone that the matrices will not be near singular. If we rewrite that, then the maximum eigenvalue over minimum eigenvalue, remember R delta is just a diagonal, adding a delta along the diagonal. So, that is very nice expression for eigenvalues or the ratio of eigenvalue. So, if we rewrite that, we get a delta lower bound, that is this guy, but we do allow for a 0 if not needed. So, you will see that sometimes this quantity will be a negative number. If R is well behaved, then this will become a negative number, and so we say maximum of this. So, if we do not need a positive nugget, then we will include 0 in it. So, if the data is well behaved for say really large theta, then pick a 0 nugget. Why do you have to enforce a positive nugget even if it says so? Okay. So, this will depend on theta. So, every time you pick a theta, so imagine in the likelihood computation for any theta when you are doing, you have to compute a lower bound. Okay. And of course, they will depend on the x too. So, we use this and try this function again. Okay. So, this guy was the MLE, and that was the estimates of the MLE. We tried it using our method, and look, this interpolates it quite well. Okay. And we did not enforce delta equal to 0 here for it. The procedure computed different values of theta, and whenever we had small values of theta, it picked a non-zero nugget, but for some values of theta when it was big, it did not need a non-zero nugget, and so it uses 0 nugget. Remember, we have this function here that this is a maximum of the two. Okay. And so, for this particular case, it is giving me a 0 nugget, but it is giving a really large theta, and it gives me a nice interpolator. Yes?
Just while you're on this picture, I agree that the fit where you have the measurements is a lot better in the right-hand panel, but if we look at the behavior at 1,
yes,
the extrapolation properties of your new process are horrible.
I agree. That's right. I totally agree to that. Yes. Well, one could say that if we have a non-constant mean trend, then that would go away, right?
Do you think that's just a symptom of overfitting generally?
Yeah, I would say so. Yes, but typically GP model do not recommend going outside the boundary of the data, right? So that's what is happening here. That here the last data point is here. If we had a data point beyond this point, then maybe we would be okay. Okay. So just because it's fitting in that it's interpolating within the data range. That's what I'd say. All right, so we tried it for a little bit bigger example. This is a 2-dimensional gold price example using 70 points maximal Latin hypercube. This is a MLE fit. So the solid curve is the true contours of the true surface, and this is the predicted contour, the dotted line. As we can see that it's doing a much better job as compared to this, but definitely this is not the best, right? This is not an interpolator, or this is not tracing the contours well in some sense. So the fit, again, we can see that for fitting this model, I used a delta belongs to 10 to the minus 5 to 1, okay, because this is a maximum likelihood approach, so I had to pick a boundary. But in this case, we got a delta estimate to be 5.26 10 to the minus 10. Okay. So this is good, it's an improvement, but perhaps we can do better. Okay. How can we do better? So far what we did is we replaced R inverse with R plus delta lower bound times identity inverse. If we look at R inverse closely, then we see that R inverse, or let's try to expand R plus ui inverse around u equal to delta. Okay, then this is von Neumann series expansion. This is very similar to Taylor expansion, but in matrix notation. Okay, so this is nothing but a Taylor expansion of R plus ui inverse. If you substitute u equal to 0, you get this quantity. Okay, just substitute u equal to 0. Now look at this and see that if you have only one term in this expansion, this is precisely that. Okay, so we recommend adding more terms in it, more terms in the Taylor expansion. So the popular approach is simply just a one term Taylor expansion. If you do more term Taylor expansion, we can do better. Okay, so we will think about how to pick M. Okay, how many terms should be added, we can do that, but that's not a big issue because we don't have to do extra computation. Yes, a tiny bit overhead is there, but we don't have to do this inversion m times or so. Okay, there is a tiny bit of overcomputation. All right, so for the same gold price function we looked at, and this is the MLE case. This is m equal to 1, only one term. If you have 5 terms, we can see that some of the features are captured here. If we have 20 terms, it is a lot better. Pretty much we captured it. So we can see that this iterative approach is quite helpful. It's getting us pretty much close to the interpolator. So that's the gold price function. We tried it for, of course, higher dimension functions too. I'm not presenting the results here because we cannot plot it. So there are tables in my paper. You can take a look. This is a real example. That was the work that motivated this. These guys wanted us to do an interpolator. So what is this? This is a map of Atlantic Canada, well, part of the Atlantic Canada. There is further east something here, Newfoundland. Okay, so this is Nova Scotia, that's New Brunswick, this is PEI, and this guy is Bay of Fundy. Okay, so some of you may have gone to SSC this year, Statistical Society of Canada annual meetings. That was here in Wolfville. It's right at this corner. Okay, this is Atlantic Ocean. This is Bay of Fundy. So here's ocean, and this tiny passage here is called minus passage. Okay, so as you can see that since there is a so narrow passage, a lot of water goes from here to here, in and out, twice a day. Okay, billions of gallons of water goes in and out. Okay, and as you can see here, this is the kinetic energy plot of the water flow here. Is very red here, very high current in the water. Because of this, there is a very high tides that we get in that neighborhood, okay, up to 17 meters. So this is a place pretty close to Wolfville, few kilometers away from Wolfville, and you can see here there is a car and everything is in the water. Okay, so because such a high tide, there is a lot of energy in the water, and so what they want to do is not a new problem. But in Canada, in the Bay of Fundy, it's relatively newer. We are exploring possible options of extracting energy from these tides, and so they are thinking about putting turbines. Where would they put? Well, of course, here is the highest current. Okay, and so they want to put turbines in there in the minus passage. So this is like a possible location of a turbine, and they want to explore the surface. Well, what surface? So they want to explore the average power surface. So some people at Bedford Institute of Oceanography in Halifax, they are modeling this tidal power, and this is a version of the FVCOM model. This is a finite volume coastal ocean model, and so they are working on this. They are using this model to explore where there are several questions that they want to answer. Where do you want to put the turbine, how many turbines shall they put, and how much power that they can extract. And so there are several questions they want to answer. So this is one of them. So they want just an interpolator of this simulator. So they gave me a 13 by 41 grid. So this we'll be looking at just this region here, not the blue shaded region here. We'll be looking at this, and we wanted to interpolate this surface. We're using a subset of these points. Okay, we will not use all the points. This is just sort of a like a reality for me. So we tried this for our approach for this example. So we used 100 points using maximal Latin hypercube, and this is the MLE, a reasonable fit, but there are some features that are not captured by the MLE. As you can see that this surface is, because of this very coarse grid that we have here, and the grid is not structured, as you can see from this plot too. The grid is not structured, the mesh. The popular approach gives me theta values and the delta MLE. Again, here I use delta goes from 10 to the minus 5 to 1 because I didn't know whether I could go 10 to the minus 10 or so. Okay. The proposed approach here gave me a theta value reasonably large and delta close to 0. Since delta was close to 0, there was no point doing the iterative approach. Right? And so as you can see that this approach, it's not so straight anymore or not so smooth. There's some captures bumps here that are being captured here, and so this is a relatively better fit, not just in terms of how it looks. I wanted to argue that this is okay too. If we look at the estimated power, maximum power, this approach gave me 1.4 times 10 to the 8 watts, and this approach gave me 1.6 times 10 to the 8 watts, and that is that a significant difference? Well, in terms of the total power, when you think about adding 20 turbines in the water, then these things will add up and would reduce eventually, say, cost of putting one turbine in the water, and one turbine is like $20 million, right? So that's a fair bit of change to save. Okay, so they wanted this. So just to summarize, so we propose a lower bound, and that lower bound. Now we don't have to worry about what should be the lower limit of delta when you are optimizing your likelihood. You can do this in the Bayesian framework too, where you're defining your prior. When you define your prior for the nugget, how do you define it? There got to be some two bounds, right? And how low the nugget has to go. So you can use this approach in that case too, and we propose an iterative approach that will lead to an interpolator. Finally, there are some remarks that, as I said earlier, that this threshold A that will vary from design to design scheme, and so we used simulation-based approach for deciding or picking this threshold. Probably there is some room to do some work to decide this threshold in a more analytic way. Okay, that's it. Thank you. Yes.
Henry. So a rather brutal way to do it would be to do a singularity decomposition and truncate the eigenvalues and just attach the nugget, a standard nugget, to the in the direction in which the eigenspace is very, very low.
That's correct. Yes.
The sort of thing they do in stiff problems in finite element analysis. Have you compared your method with something like that?
I have not compared my results, but I've seen that method. The first time I saw that method was in Jones et al. Paper, where they do singular value decomposition, and I have implemented it, and I noticed that one of the problems that in that particular method is what is the lower threshold that you pick. Okay, so when you start throwing away the lower eigenvalues or the crappier eigenvalues from the bottom, the maximum would be fine, but the smaller one, where do you start? Where do you chop off? And you say that I will keep these eigenvalues for my singular value R inverse.
The trouble is that delta I, the identity, kind of smears the effect over all possible eigendirections, and therefore you're not using your delta efficiently. Because why delta I, why not delta times a diagonal matrix, suitably chosen to have almost the effect of
right.
singular.
That's an interesting idea. I hadn't thought about that.
Other questions?
Yes.
Yeah, I just would like to take that opportunity to make a point about the term nugget effect, because I looked at the literature in geostatistics, and actually what they call a nugget effect is within the correlation, which means that you have automatically an interpolator when you have nugget effect. I think what you mentioned here is more the noise variance, in the sense that your term delta, or what is sometimes called tau square, is in the matrix, but not in the vector of correlation, which makes it not interpolating. But if you have a nugget effect and it's present in both the vector and the matrix, which makes algebraically the predictor and interpolator anytime.
Okay.
Another interesting. Okay, let's thank the speaker once more.